Next is carrier of current. What is carrier of current? Carrier of current means which charge particle is carrying the current. Okay, which charge particle is carrying the current. So you would see that in metals, you have free electrons, and the free electrons actually flows, the electron flow. So in metals, carrier of current is this electron, because it is only the electron which is flowing. Free electrons are flowing in the current. But when you do electrolysis, okay, when you do electrolysis, you have done electrolysis in chemistry. So in the electrolysis, what happens? There is a cation and anion, positive, negative charges, and they both move towards the respective electrodes. Okay, they both move towards a respective electrode. So if you have a negative charge, it will move towards a positive plate. Negative charge move towards the positive plate. Positive charge move towards. So both of them are moving. So here you will say that the cation and anion both are carriers of current. Both are carrier of current. In the last chapter, semiconductors. In semiconductor chapter, you will learn that there is something called hole. So hole behave like a positive charge. Hole is not a positive charge. It behaves like a positive charge. We will do this when we do this chapter semiconductor. So hole also moves. When there is an electric field apply, hole will also move, but it will move like a positive charge, but it is not a positive charge again. So if in semiconductor, if I ask you what is the current carrier, so hole will also become a current carrier, and electron as well. So hole, electron. So you have to be very specific in identifying what are the current carrier for different cases. Now next is mechanism of current flow. Mechanism of current flow in a conductor. Drift velocity, relaxation time. This is a very important topic. Now think about the conductor. A conductor has a large number of free electrons. Let's say you have a cube of metallic, and you have large number of electrons here. Now all these electrons, free electrons, I'm talking about the free electrons. Now these free electrons will have some velocity. Why? Because they are all having certain temperature. You know that at a certain temperature there would be kinetic energy of the particles of the system. All this thing you already know. So these electrons will have some velocity, and that velocity we call thermal velocity. Why thermal velocity? Because obviously it is because of the temperature. Now this thermal velocity is random. This thermal velocity is random. So random means that these electrons would be moving in any random directions all the time, and they don't individually, they are moving randomly. Individually they are moving randomly, but collectively they don't have any direction. Okay, collectively they don't have any direction. So they are moving randomly, collectively they don't have any direction. Then that means you can write this expression for their velocity. So their velocity, okay, the net velocity will be equal to 0, individual sum of the vector sum of the individual velocities of all the electron divided by the number of electron. And then you will find that there is no net flow of charge in any direction, because they are just moving randomly. Now if you apply a electric field, If you apply this electric field, let's say you pick up this conductor and then you apply an electric field from on this conductor. How do you apply electric field? You just put a potential difference across it. So when you put a potential difference across it, what will happen? Let's say like this. Now, because of this potential difference, now there will be an electric field that is set up within the conductor. This electric field will be in this direction. Okay, the electric field will be in this direction. Now, because you have set up an electric field in the conductor, so these electrons would be experiencing a force. So let's say this is your conductor, and this conductor is provided some potential difference, and due to this potential difference you have some electric field being set up. Okay, or has some electric field in setup, and because of this electric field, what will happen to electrons? They were moving randomly, that is okay, they were moving randomly, so that's not that they are going to leave their random motion, but they will start experiencing an extra force opposite to the direction of the field. Now this force will be what we know, that the force experienced by the charge in an electric field is equal to Q times E. You know this from the first chapter itself. So this Q will become your charge E here. The Q, I'm going to write it as charge E because charge of the electron into electric field. And the acceleration due to this force will be is equal to the charge into the electric field divided by mass of electron. Again, we are finding the acceleration for the mass of electron. Okay. So how does this acceleration affects the whole motion? How does this acceleration affects the whole motion? So in the presence of electric field, each electron experiences a force minus of QE in the opposite direction to the electric field and undergoes an acceleration QE by M minus again here. M is the mass of the electron. As the electron accelerate, now this point is very important, read it very carefully. As the electron accelerate, they frequently collide with the positive metal ion and other electron of the metal. So the electron path is not like this. The path of the electron is like zigzag, 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 because they are consistently colliding with some metal ion and other electrons. They're consistently colliding at all these positions. They are basically colliding with something. So lot of collisions are experienced by electron while they are moving through the conductor, and these collisions are with what? Metals, ion and other electrons, both. Between two successive collisions, the electron gains the velocity, because after colliding every time it is going to lose its velocity and then it will gain its velocity. How does it gain the velocity? Okay, because of the electric field. So electron gains a velocity component in addition to the random velocity, as I told you. So random velocity will be there because the random velocity is because of the temperature, that is the thermal velocity. So in addition to the random velocity, there will be some velocity component here, and it is will be all in the opposite direction to the electric field. However, the gain in the velocity lasts for short time, because whatever the velocity, if an electron gains some velocity and collide with another electron, it will lose it. Collide with another electron, it will lose it, and it is lost in the next collision. So at each collision, the electrons start afresh with a random thermal velocity. Pause the video, read this whole paragraph once again, try to visualize this. Try to visualize this, that what exactly is happening. Now we are going to understand how to calculate this velocity, this particular velocity, how to calculate, because eventually all the electrons are doing this kind of motion. So if you look at one particular electron's path, this path might be like this, collision, 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 again collision, again collision. And consistent collision electron is doing, and not just one electron, all the electrons are doing like this. You can visualize how many numbers of electrons are there in a conductor, and if all of them are doing like this, so many numbers of collision is happening. You see, individuals electrons are moving very fast and colliding and everything, but collectively all the electron, collectively all the electron, collectively all electrons are moving with not so very high velocity. They are moving with something called drift velocity. They're all moving with something called drift velocity. Drift velocity is not very high. It's actually very slow. And drift velocity is not the velocity of individual. Drift velocity is not the velocity of individual electron. It is a collective velocity of all the electrons. So that is what we have to find. We have to find the expression for this drift velocity. We are going to find the expression for the drift velocity. How to find the value of drift velocity? Now, if we keep on taking the velocity of individual electron, let's we take the velocity of one electron. So every electron will have their velocity due to this motion, this electric field. So when you write the velocity expression, what will you say? You'll say the final velocity is equal to the initial velocity plus acceleration into time. Simple. Now this initial velocity of all the electron was the thermal velocity. Remember the thermal velocity, because that was there due to the temperature. So the final velocity of all the electron, or any velocity, like velocity of the electron when it is accelerating in the electric field, will be equal to acceleration into time. So V final, or V velocity of any electron, will become initial velocity of the same electron plus acceleration due to this electric field into time. But what is this time? This time is written as a symbol tau. Okay, this time is written as a symbol tau, and tau is the relaxation time. So we'll be discussing this here. Okay, this is relaxation time. So we'll discuss this relaxation time in detail. For now, only understand that this relaxation time is the time between two successive collision of electron. For example, if an electron comes here, collides here, and then goes here and then collide here. So in this particular motion, the electron, when it is coming here, it is colliding here and then going here. So this here, the time between the two successive collision of electron, this time here, this is called the relaxation time. Okay, so time between the two successive collision is the relaxation time. Now if you go through this whole thing, whole derivation, this is the velocity of the first electron, so is the velocity of the second electron, and you can have the velocity of the third until nth number of electron you can calculate. Drift velocity, as I said, is just the drift velocity is the collective velocity of the electron. So when you calculate drift velocity Vt with a vector sign on the top will be is equal to the vector sum of all the electrons, all the electrons divided by the number of electrons. And then you can keep on doing this. V1 is equal to initial velocity 1 plus alpha tau and so on, and eventually you will get this expression. Now remember, this value was already 0. We have done this before. This value is already 0. The net thermal velocity of all these electrons is equal to 0. Okay, this one. The net thermal velocity of all these electrons will be equal to 0. So in this expression that we are doing, this whole value becomes 0. And what is left is this. So acceleration becomes here, and this is the relaxation time, but not just the relaxation time for one electron, but the relaxation time, collective relaxation time or average relaxation time for all the electron. Okay, so this is the average relaxation time of all the electron. So the average time that elapses between two successive collision of an electron, okay, this value here, average relaxation time, and your drift velocity then will become acceleration into tau. Acceleration is a vector. Now, acceleration is minus of E charge into the electric field divided by the mass. This we have done before, into tau. And this is what your expression for drift velocity is. So the drift velocity of electron, it may be defined as the average velocity gained by the free electrons of the conductor in the opposite direction to the externally applied electric field. Very simple definition. Now read this paragraph very carefully. Although the electric field accelerates an electron between two collisions, yet it does not produce any net acceleration. This is because the electron keeps colliding with the positive metal ion. The velocity gained by it due to the electric field is lost in the next collision. So as a result, it acquires a constant average velocity. What does it mean? It means that the electrons, when you are putting the electric field across a conductor, the electrons are not collectively individual. I'm not talking about the individual electron, but collectively these electrons are not accelerating. Collectively, they all have a velocity which is drift velocity. So don't imagine that the electrons are accelerating. When the electrons are flowing through a conductor, they are flowing at a rate of drift velocity, which is an average constant velocity, opposite to the electric field. Now, this is a very nice diagram for showing the drift, how the drift thing happens. So you see this, and why it is called drift also, you will get to understand. Uh, the slow and steady drift of an electron in the opposite direction to electric field. Okay, now the solid line represents the path in the absence of field. That means if the field was not there, then the electron random velocity, thermal velocity would have made the electron go in this path. But because of the electric field, this path is changed and a dashes line in the presence of the electric field. So electric field will increase the drift. Okay, this extra distance that will keep on traveling. And now imagine if all the electrons are doing this, that is why this particular velocity is called the drift velocity. Okay, then extra distance the electrons are traveling other than what distance they were traveling because of the thermal velocity, the extra distance they're traveling because of the electric field applied. So that's called the drift. That's why drift velocity.